In this video, we're going to look at the Newton-Raphson method for finding roots. Note that if you're looking for information online about this, sometimes it's just called the Newton method. The problem with that, though, is that Isaac Newton was pretty busy and he was producing lots of different ways to do lots of different things. So you'll find different algorithms that are just called the Newton method. If you call it the Newton-Raphson, you're more likely to find in particular what you're looking for, which is probably how you found me. Note also that we're not restricted to using this just for finding roots. We also can use it to solve other forms of nonlinear equations. For example, if you had x cubed minus 4x squared equals 15, and you want to know what value of x solves this, or a value of x, I should say, well then, if we subtract 15 from both sides, now it's just a root finding problem, right? Because here's the polynomial is equal to 0, find the roots of that. So we can use it for both. Now in a previous video, I used the interval bisection method for finding roots or solving nonlinear equations in that case. And it worked basically like this. If this is x-axis and say that's my function, we have to know an interval in which the root lies, or at least one root. So let's say that over here I have, say, 10, and over here is 0, and I know there's a root somewhere in here. Well, interval bisection is going to calculate the midpoint, and now it's going to move one of these two endpoints to here. It will be able to determine that the root is to the right of this, so it's going to move this interval in. So this now becomes the interval. Now it's going to calculate the midpoint of that. Do the same thing again. It's to the right of this. So now this becomes the new interval. Keep doing that until you reach a certain level of tolerance for the distance between the intervals, or the boundaries on the interval, I should say. Okay? There's nothing necessarily wrong with that. But if we look at this particular function and say, well, what if I happen to believe there is a root close to 10? This function drops down pretty fast. So is there some way to say, hey, look over here for the root instead of going or looking through this entire interval? Well, it turns out there is, if we incorporate some information about the function into our process, which is what Newton-Raphson does. So let's see how that works. So let's say that once again we have something like this, and we have this function, and we think that x1 here is close to the root. Well, if we were to go up to this point, and the y value here will then be f of x1, right? That's the y value here. If we have a tangent line at this point, that represents the slope of the equation at that point. So if we extend that, sorry, my drawing's not real good, we could come down to here, and this would be x2. Now, where I've drawn this is actually above the function here. So if I were to come down to here, we then would have f of x2, draw a tangent to here. Then we have x3, repeat the process, come down, and keep cycling through, and hopefully get to a root. But once again, the difference between this and the interval bisection method is that the slope of the function is used to try to speed up the process. It's not a guarantee. A bad guess for our initial value can result in either it taking longer than interval bisection, or maybe even not even converging to an answer at all. And we'll see examples of that in a moment, because I'm going to show you a Python program that I wrote to demonstrate this. So how does this work? Well, no doubt at some point when you were learning about algebra and basic geometry and stuff, you saw the equation for a line. You say, okay, find the equation for a line in the form of y equals mx plus b, and m here's the slope. And maybe you were given 2 points. You were given x1, y1, and x2, y2. And so you know that then m is equal to x1 minus, y1 minus y2 over x1 minus x2. Or you could reverse these and you still get the same answer. So what's the slope we use here? Well, here's x1. Here's f of x1, which would be this. Okay? And the slope at this point for this tangent line is the derivative, right? This is f prime at x1. That's the slope at this point. So we'll have this right here. And so now if I rearrange this, let's rewrite that to make it a little easier to see. Have f prime of x1 is equal to f of x1 minus, what's y2 here? Well, y2 is going to be 0, right? Because we're looking for a root here. So this is where, if we call this the y-axis, and this was the x-axis, the y value here is 0. So that's that. We have x1 as our initial guess, but what is x2? We don't know that. Well, that's what we're trying to find. Because we'll have x1, we know the function, so we can find f of x1, and if we can find the derivative of that function, then we can find f prime of x1. So now if we rearrange this, x1 minus x2 is equal to f of x1 divided by f prime of x1, right? Because I was just subtracting 0 right here. Now I have minus x2 is equal to minus x1 plus f of x1 divided by f prime of x1. And now I multiply through by negative 1, and I get x2 is equal to x1 minus f of x1 divided by f prime of x1. That's how I would find x2 here. So then how do I find x3? Well, now we basically just do this. We say, okay, using this form, we would have x3 is equal to x2 minus f of x2 divided by f prime at x2. And we can keep repeating this process, but the overall form then will be x of k plus 1 is equal to x of k minus f of x of k divided by f prime of x of k. We're just going to iterate. We're going to guess what x1 is, use it to find x2, then use x2 to find x3, use x3 to find x4, and so forth, with the idea that we're getting closer and closer to the root, assuming that we converge. So now let's look at a program that I've written to demonstrate that. So this is written in Python. I've imported a couple of libraries that I'm going to use below. NumPy is a numerical library that happens to have a root solver, so I could use it outright just to get the same answer we're about to get. In fact, it will find all the roots. But I need it below because it also has support for vectors, and I'm going to use that for plotting. Then matplotlib is the plotting library. Then I'm creating two functions here. F of x is the function that we're processing. It's minus 3.55 times x cubed plus 1.1 times x squared plus 0.765 times x minus 0.74. And then the derivative of this is right here, minus 10.65 times x squared plus 2.2 times x plus 0.765. Note that I got this original function from this link because it's difficult to find functions that will demonstrate the problem of convergence that I want to demonstrate here. Okay, so I had to sort of borrow their function here. Down below, we have my initial guess. It will be -1. And then in order to keep the function running until we reach a certain level of tolerance, I need to be able to also store the previous value, which I don't know yet. So I'm just going to add 1 to this value to give us a difference of 1, which will be much greater than 10 to the -5. That will get me into the loop, and then after that, we'll start using previous values. And then the loop counter is just here to show us how many iterations it took. This is the actual code. So it says, as long as the absolute value of the difference is greater than some tolerance, I'm going to print the current values. I'm going to save the current value as what will become the previous value, and then I calculate a new value using the function we had before. F of p is f prime at x, and then update my counter. So I use absolute values. Well, I don't know which of x or previous will be biggest. Okay, so it could be that I'm producing negative numbers here, even though the gap between them may be pretty large. So I take the absolute value. And then at the bottom, I have the code necessary to plot. So I'm going to take the last value of x, plot that onto my graph as the root, and then this will draw the function itself. So let's run my program to see what happens. And our initial guess is -1. So there's the function. Let's make the graph bigger. There's the root, because here, this is the x-axis. So we're looking at this range, -1 to +1. And there's the root. And we found the root, which is -0.608, found it in 4 iterations, as we can see here. So because I started with -1, and then on one iteration I found a new number, second iteration is another number, and so forth. Okay? Now let's start with +1 as the initial guess and see what happens. Because what happened the first time while we're here? This is -1. So the tangent at this point came down, well, it says it came down to -0.739. So that's about right here. So the slope came down to about here, went up, slope came down, went up, slope came down. Now if we're choosing this value, the slope is going to go way up here, then have to come back down and so forth. So let's change that to +1. And now we know what the plot looks like, but it took 61 iterations to get to the answer. That's much more than before. And offline, I used interval bisection to also try to solve this problem with a tolerance of the interval width of 10 to the -5, and it got down to an interval of that width in 18 iterations. So it was actually better for this initial guess. Okay, so this does demonstrate that the initial guess is important in terms of how long it takes to solve. But now let's split the difference on the initial values. Let me show you the plot again. So we started with -1 as initial guess. Then we tried 1 as initial guess. Let's try 0 as initial guess. And this will show why I had to find a function online that had a problem. So my initial guess now is 0, and let's run the program. I'm going to stop this because it's never going to stop on its own. So that's 732 iterations. But if we look closely at the numbers, we can see that these same 3 numbers get repeated over and over again. For this particular function, it just cycles back and forth between these 3 numbers if my initial guess is 0. So it never converges. And there's other values for which it could have problems. Let's try 0.5. I think that will also have a problem, if I remember correctly. Yeah, that also has a problem. And there would be some others, but each of these demonstrates a problem in terms of convergence. It's never going to converge with that initial guess. So what you could do is, if your first guess doesn't work, pick something else that you think will work. Like, this isn't that far from values that didn't work, right? -1 or +1 or whatever. I don't know if this will work. Let's try 0.75. And yeah, that worked. And it also only took 4 iterations. But this is very sensitive. And to show you why it's so difficult to come up with an equation that demonstrates that problem, let's change the original function slightly. Let me delete this number right here. So I'm changing the first coefficient, the one on the x³ term. I'm changing it by removing this value, the 0.05 part of that. Now note that will change the roots of this slightly. So let's run it again. Remember, 0 as initial guess for the previous version did not converge. But now this converges. Now the root that satisfies this is negative 0.610 or 611 if you'll round off, whereas before it was 6 or negative 0.608, but that took 37 iterations, all by making that slight change. So all these are factors in terms of how well this algorithm performs. But once again, if you have a good initial guess, like we did here, it doesn't take very many iterations to get to a good quality estimate. And this is just an estimate, right? If I let it keep going, if I change the tolerance, let's make it 10 to the negative 8, it will take more iterations, of course, because we're saying the difference between consecutive values has to be even smaller. They still don't find a solution. So it added one iteration to get something that's even better, because these are the same at this digit, this digit, this digit, this digit. Here's where they differ between the 5 and the 4. And if I change that to 10 or negative 10, actually the same iterations. Let's see if I make this say 15. And we're getting on the bounds of what would be possible, actually. That took 6 iterations. So even though I'm looking for a much better answer in terms of how many digits of precision, it didn't change much how many iterations it took. Versus if I now go to this, I don't know how many that's going to take. Let's see. 62. So I think it took 61 before, so that also didn't change much. So there's an example of the Newton-Raphson method for finding roots of an equation.